Bismillahirrahmanirrahim. In this video, we'll talk about basics of bipolar junction transistors, BJT. And as we know, that the transistor has three regions, the collector region, the base region, and the emitter region. And primarily, we'll be discussing with NPN transistor, but the similar rule applies to PNP transistors. Now the emitter supplies electrons, base controls the flow of electron between emitter and collector collects the electron. Okay, and see this is the same circuit I have drawn. In the base we are supplying with the positive voltage. This is for NPN case again. Emitter supplies electrons, so the negative portion is connected to the emitter, and collector collects electrons, so a positive terminal of the battery is connected. So they are the same here, but we'll see what is the difference between the three models. Now if we short circuit the base or make the base grounded, then this will be called common base. So the base is common to ground. And if we short circuit the emitter part, emitter battery, then the emitter is directly connected to the ground. So this will be called the common emitter. And if the same circuit we short circuit the collector battery, then the collector is now grounded. So this is called common collector. Now this is a simple way of explaining, and now you can see the actual circuits, which are basically functionally they are same, but they have been drawn differently. You can see there is a VCC, as we are saying here, and there is a VE, and the base is grounded. Same here, the emitter is grounded here, and the other two supplies are there. And in this case, this is collector, so collector is grounded. So now we have seen the three configurations. A simple point I would like to highlight, that is the input-output relation. In this case, you can see that the input will be given at the emitter terminal, and the output will be taken from the collector terminal. So input is E and output is C, collector. Here input is at the base and the output as the collector. And in case of a common collector, the input is at the base, but the output is at the emitter because collector is grounded. And in all three cases, this formula is valid, that the total current, emitter current, is equal to sum of the collector current plus base current. Okay, now let's see the common base configuration. I'll not go into much details, but this is the circuit that we have discussed, and we know that the input is at the emitter terminal and output is at the collector terminal. So we try to find relation between I emitter and I collector. And this is the equivalent circuit, you can say. I prefer to draw it like this. This going out, I hope you know that NPN, some people call it not pointing in. Now this is not pointing in, pointing out. So this symbol is for NPN. Okay, now there are characteristics curve. This curve is between the VBE and IE. So VBE is the base emitter voltage. This is the base, this is emitter, or here VBE. So between VBE and IE, the emitter current, you can plot a graph for different VCB, for different voltage of VCB, and the graph will be like this. This is not much used. There is another graph which is commonly used. This is called the output characteristics curve. Now this is between VCB, the collector and base voltage, in case of a common base, and between collector current. And now if you look at this carefully, these are for different currents. The emitter currents here is 0, so this is almost on the 0 line. But when you increase the emitter current 1 milliampere, the graph becomes like this. That means when you keep on increasing the VCB, the graph initially increases and then it remains almost flat. And as you increase the IE current, it just shifts its level, it goes up and then remains flat. And this portion here is called active region. We'll discuss this later on. This is called saturation region and this is called cutoff region. So the first thing we can approximate is that IE is equal to IC is equal to IE. The formula we have seen that IC is IE is equal to IC plus IB. We assume that IB is very, very small, and therefore we can approximate that IC is equal to IE. So this is an approximation. Then VBE is assumed to be 0.7 volt fix. And then we define here what is known as the gain, that is called alpha, and it is the collector current divided by emitter current. And now since collector current is slightly less than emitter current, therefore alpha or alpha DC also called will be less than 1. It will be around, let's say, 0.95, 0.99, etc. One important point to note here is that when IE is 0, if the, like here in this region, when IE is 0, then no forward current flows, but a reverse current flows from collector to base. A reverse current will flow from here, collector to base. This is called ICBO or ICO. So this is called reverse saturation current. So keep it in mind, this is due to minority carriers. And from here we can write that alpha C, the collector current is, IC, the collector current is equal to alpha IE. And also we can say that collector current is alpha IE this plus the reverse saturation current that flows from collector to base due to minority carriers. So this is a more accurate representation. And then there is another term which we will not be using now, but just for your idea, there is an alpha AC which is delta IC divided by delta IE, that is slight change in IC divided by slight change in IE when VCB is constant. So this is called alpha AC. Okay, now let's see example 15, end chapter problem number 15. Question is, given alpha DC 0.998, determine IC if IE is 4 milliampere. And part 2 is determine alpha DC if IE is 2.5 milliampere, IC is 2.75 and ICBO is 0.1 microampere. The first part, we know it's very simple. You know this formula. We can just straight away put in this, or we also know there's another formula that alpha is equal to IC over IE. From that also you can get this. So the value of alpha is given, we put in that, value of IE is given. So IC is 3.992 milliampere. Now we come to the second part. And now there are two formulas. One is IC is equal to alpha IE. This is a kind of a approximation. A more accurate formula is this one. IC is alpha IE plus ICBO. Now ICBO is the minority carrier current. Now since in this question ICBO is given, therefore we will be using the second formula. We used the first formula in part 1, but in this case we will be using the second formula. So from here we can find alpha to be IC minus ICBO divided by IU. I hope you can find this from this formula. And now we put in the values. IC is 275, ICBO is 0.1 microampere, and I is 2.8. So putting in the values and solving, we get alpha to be 0.9821, which is more accurate. Okay, now we come to the common emitter configuration. Now common emitter, as we have seen, that the emitter is grounded and the input is now the terminal B, or the base terminal is the input, and output is collector terminal. So we'll try to find a relation between IB and IC. In the previous one we found a relation between IE and IC. Here we'll try to find a relation between IB and IC. Now there are two curves, similar curves that we had. This is the base characteristics. Now this one is between VBE and IB, and given VCE, different values of VCE. So VBE is the base emitter voltage, and the IB is the base current, and VCE is the collector to emitter voltage. For different voltages we get different curves. So this is called the base characteristics curve. The other curve is called the collector characteristics curve, which is again between VCE and IC, as we saw in the previous example also, and for different values of IB. Now as we keep on increasing IB, this graph moves up, but then it's generally a very low slope this graph has. And we'll study this in the next video, the details of the active region, etc. One important point which we'll be discussing here is this area from 0 up to this is called the, or due to the ICEO or ICBO. This is the collector emitter leakage current, from collector to emitter leakage current when in the cutoff region, when IB is 0. So this we will be using. Okay, this formula remains same, and this also we saw, and this also we saw IDC. Now from here we'll derive, from the detailed formula that we had, we'll derive an equation. In IE we replace by ICIB from here, and simplifying we get another relation of IC in terms of alpha. So we'll use this relation. Now when IB is 0, so in this case when IB is 0, then we'll have ICBO divided by 1 minus alpha. So IC is ICBO divided by 1 minus alpha when IB is 0. Okay, the resulting collector current is called ICEO. So this current now is called ICEO, which we saw here. And the name is ICEO, but it is actually ICBO divided by 1 minus alpha, or it is multiplied by beta. Okay, now we are defining a new term called the beta of the transistor, or beta DC. Now this is IC divided by IB. Note, in the previous case, in the common base case, it was IC divided by IE, and we had call it the alpha gain, and now it will call beta gain. Beta is IC divided by IB, and since IB is very small in microamperes, therefore this value is going to be quite large, somewhere from 100 to 500. Okay, and like in the previous case, we can also define beta AC, which is minor change in the AC divided by minor change in IB. And again, from alpha and beta relation, we can calculate this formula, that alpha is beta divided by beta plus 1, or beta is alpha divided by 1 minus alpha. The calculation is shown in your book. You can follow that. And also, the collector leakage current is approximately equal to beta ICBO from here. You can see this is beta. So instead of, it is 1 over 1 minus alpha instead of alpha divided by 1 minus alpha, and that is by the approximation sign. And finally, IC can be written in terms of beta IB, and IE can also be written in terms of beta plus 1 IB. So these formulas you have to keep in mind. Now let's solve a problem. For the common emitter characteristics of figure 313, find the DC beta at the operating point of this, then find the value of alpha, and find at VC6 find the corresponding ICO, and calculate the approximate value of ICBO. So the first one, we have to find the DC beta. So DC beta is IC over IB, and let's see the characteristics curve. Okay, now the IC is 2 milliampere, that is given. IC is 2 milliampere. How much is IB? If we know IB, then we can find beta DC. And we can find IB from the graph. Okay, so this is the graph. VCE is 6 volt and IC is 2 milliampere. So this is VCE scale. So this point is approximately 6 volt, and this is IC, so this is 2 milliampere. So they cross at a point where we have to find value of IB. Now you can see we have one value of IB given as 10 microampere, and the other slightly up is given 20 microampere. So in between this, and if you consider this 5 divisions, so it is almost 1 division less. So we can say that IB in this case will be 18 microampere. So IB we take as 18 microampere, and now plugging in, we find the beta DC to be 111.11. So this is the first part. Then it is saying find value of alpha corresponding to this operating point. So we have found beta. We know the formula, the relation between alpha and beta. So alpha is beta divided by beta plus 1. So we put in the values and we find alpha. And then question 3, at VC6 find the corresponding value of ICEO. Now this is 6 volt. So if you look here, this is the gap which is ICO, and this gap is how much? It's about 1.5 division, so we can say it is 0.3 milliamperes from here to here, 0.3 milliamperes. So this is 0.3 milliampere. I think it should be microampere. Oh, sorry, yeah. So this gap, if you look in the C scale, because it is IC leakage current, so we'll see the IC scale, and from here it is about 0.3 milliampere. And finally, ICBO, this is the formula that we'll be using. ICO we have got from here, alpha we know, 1 we know, and so ICBO is 2.68 microampere. Okay, and finally we come to the common collector configuration. So collector is common, and this is the circuit where collector will be grounded. And here if you see, the input is at B and output it as emitter terminal. Now for all practical purpose, the output characteristics of the common collector configuration are the same as the common emitter configuration. So we will not go into. Okay, let's have another question for common collector. Question number 26. An input voltage of 2 volt RMS measured from base to ground is applied to the circuit, assuming emitter voltage as follows. Emitter voltage follows the base voltage. That means if when the base voltage goes high, the emitter voltage also goes high. When the base voltage comes down low, the emitter voltage also goes low. So that is the following the base exactly. And then VBE, base emitter voltage, is 0.1 volt. We have to find the amplification gain, voltage amplification, and also we have to find the current through the resistance RE. This is RE in the emitter, which is 1 kilo ohm. Okay, so let's first of all redraw the circuit by incorporating some of the data that has been given. This VB is 2 volt RMS, and when we say VB, it means it is referred to ground. So VB and ground is 2 volt RMS, and this terminal is also called the input terminal. So VB is equal to VI. VBE, voltage between base and emitter, is 0.1 volt RMS. And this here at point E, the voltage is generally called VE, but since we are taking output from here, so this is also our output voltage, VO. Okay, now VO, from here we can say that VO, this voltage is actually this voltage minus the voltage here. So we can say that VO or VE is actually VB voltage, VV from here to ground, minus this one. So 2 minus 0.1 is 1.9 volt RMS. So this is the output voltage here. And now we can find the current simply by dividing by the resistance. So 19 volt, we get the amplification. This is the output voltage. We know the input voltage 2 volt. So V out over VI is the amplification. So 1.9 divided by 2 is 0.95 is the amplification. And now the current IE is VE over R. VE is the output voltage or V emitter, which is 1.9, and divided by R is 1 kilo. So it is 1.9 milliampere. So I hope this gives you some idea about the introduction to transistor and common base, common collector, and common emitter cycles. Thank you.